So, we were considering the passive architecture, and we considered number of devices like solar cookers, solar stills, etc. And then we also were considering the so called overhangs and wing walls. The whole idea of, if you have got a, in the end view, this is the window and this is called the overhang. So, this will not let the sun shade it. Over a certain area, the remaining thing can be lit. And of course, you may also have a window of certain thing, then a wall, and the overhang may be after a certain gap G. Still, this may cast a shadow over certain part of the window, and consequently, this could be useful in summer and particularly in tropical climates in stopping the solar radiation entering the room, and in winter because the sun is pretty low, as I have explained in the last lecture, it will allow the sun's rays to enter the room. Now, in the context of so called utilizability, which we said that the solar radiation intensity above a certain critical level shall be useful for meeting the energy demand above a particular specified minimum temperature. But in the case of passive heating, the solar radiation above a certain level comparable to the T minimum equal to T comfort is not utilizable. In other words, when once the room is at T comfort level, any solar radiation above that level shall not be utilized, and hence the concept of unutilizability. So, this on different time scales it will be simply 1 minus phi or 1 minus phi bar. If you have calculated utilizability, unutilizability will be simply 1 minus that utilizability. So, that is what I have put down here, phi on equal to 1 phi or phi bar on equal to 1 minus phi bar. Okay. And we know the methods to calculate phi or phi bar, monthly average or daily or a hourly average. So, in that context, the solar radiation available to you above a particular critical level shall not be utilizable to heat the room, because it overheats beyond the comfort condition. The concept is the same, the methodology of calculating phi bar remains the same. However, that energy is not useful for contributing to heating the room, because it overheats. So, these overhangs and wing walls achieve prevention of solar radiation entering when not desired or desired, it can be interpreted both ways, and allows when needed. And there are a number of calculations, number of concepts, and one of the references is 57, which I will give you at the end of these lectures, and then 58, our own work, contains the method of calculation of what we call the shading factor, which will come just now. So, now you have got a what is called a shading factor. When the window is shaded by the overhang or the wing wall, a part of it will not receive the direct solar radiation. Consequently, the radiation that is likely to enter through transmittance of the glass cover will be impaired by the factor which we call the shading factor, since the entire window is not exposed to sun's radiation. So, now you can have that shading factor just to distinguish between our solar load fraction, and this is actually I stands for illuminated area. It can be short term like an hour or a long term over a period of 1 month or a day. So, we have also described in the last class the types of shadows that can be formed. The overhang in general is at least the width of the window, where HW is the height. This could be the projection P. So, this, without showing the clumsy way, casts a shadow right when the sun is in front of it like this, shaded. This is only to recapitulate what we did earlier and to emphasize the complexity involved in calculating the shading factor, though it is very easy to understand that a projection will cast a shadow, and it could be like this. Okay, this is the shaded area. It is not the overhang, but the shadow shape goes beyond the window, and I can have a degenerate case that this line shall be up to here and then proceeds. We are not really interested in what happens further. So, this is a triangular shape where the end of it, edge of it just coincides with the edge of the window, and the third last could be let me go like this. So, looks triangular, but the again it becomes horizontal beyond the window width W. Okay. So, it is a complex thing, it depends upon the time of the day, of course, then the location or the day of the year. So, what is it we want to do is solar radiation falling on the shaded surface. Whatever I have illustrated are also true for the wing wall. If this is the window, I may have a wing wall like this and another one like this. So, if tentatively I assume this is south and this is east, and hence this will be west, either this or this will cast a shadow depending upon its forenoon or the afternoon. So, the shading factor can be defined as the ratio of the if you look at it like this, I am interested in this part, this is shaded, and the remaining area is lit by the sun, and AW is the total window area. So, we might define Fi, the instantaneous shading factor. So, this is what I tried to do it in terms of the figure, that hatched portion represents the shadow and the non hatched one is the actual projection. So, this will be equal to A lit by AW. So, this is written in such a manner that actually it may be the, instead of the shading factor, it could be the lit factor. If A lit is equal to AW, Fi is equal to 1. If Fi is equal to 1, that means the window is not shaded. In Fi is equal to 0, it is completely shaded. So, if you want a long term, you can always have Fi bar integral I b r b Fi d omega upon I b r b d omega. Just like we have defined your r b bar as integral I b r b d omega by I b d omega. Okay. This is the total amount of solar radiation falling on the collector, which is shaded by a factor which changes with time by the total solar direct radiation that is likely to fall on the window or the surface if there has been no shading. So, the shapes we have already described, it could be triangle, rectangle or trapezoidal. So, this is the equation which I have already written, Fi bar. Now, both the numerator and the denominator will be from apparent sunrise to apparent sunset angles relevant to the particular window under consideration. So, if I try to write the solar radiation received by the window per unit area of the window, so IT into AW is the total quantity of the solar radiation that the window is receiving, should be equal to IB RB multiplied by only the A lit, because the beam radiation does not fall on the shaded area, times the diffuse radiation 1 plus cos beta by 2 times AW plus rho ground reflectance multiplied by I into 1 minus cos beta by 2 into AW, where beta in general equal to 90 degrees, not approximately, let me put it this way, in general. But it is not essential that beta be 90. There are quite a few architecture buildings where the window or the glass frames are not at 90 degrees, they are at a particular angle. So, if I try to calculate IT per unit area of the window, that will be equal to IB RB A lit by AW plus the diffuse component plus the ground reflected component. So, this we shall call it IB RB Fi, the shading factor, plus these are very familiar terms for us, should be by now. Okay. So, that is it here, yeah, I have divided throughout by AW. So, this is, if I extend this just like we have done it for the just simple radiation unshaded, H t should be equal to H b R b bar F I bar. It is something like absorbed radiation, except that this is a shading factor times the diffuse radiation plus the ground reflected radiation. Okay. So, under extraterrestrial calculations, just like we have done for R b bar, so which I will indicate by suffix additional O will be omega S r to omega S s, and G 0 R b F I d omega upon omega S r omega S s G 0 R b d omega, right. So, G 0 is something like G 0 we know equal to G O n cos theta z, right. That analytical expression is known, and still we do not know F I, though R b is known to us. So, this F I bar 0 will be, if very close to F I bar, if K T is uniform, not necessarily equal to unity. This we have proved in the case of R b bar, looking at the success, why the terrestrial calculation is yielding sufficiently accurate results as the extraterrestrial calculation. The other way around, extraterrestrial assumption is good enough for the terrestrial conditions also, and we found that if K T not necessarily be equal to unity, but if it is uniform, it will be quite acceptable, and it will be exactly equal to the calculations we made under extraterrestrial conditions, right. And K T is more or less uniform when the solar radiation is high, in general let us say 10 to 2 p.m. Consequently, this will be acceptable as a good approximation. Now, you have the problem of that shaded area changes shape and of course, size. So, that in other words, this so called omega S r to omega S s may have to be split up into omega S r omega 1 plus omega 1 to omega 2 plus omega n to omega S s. So, it keeps changing from rectangle to trapezium to triangle, triangle just truncating at the edge of the window and going beyond. So, this is a little complicated issue, and we need a thorough perfect algorithm to find out the area that is lit. And if your windows are not vertical, if they are at an angle, the problem is even more compounded. But if you have an infinite overhang, as I have shown over here, so this may be 2 to 5 times the window. The shaded area A s is always a rectangle. So, this gives us some respite. So, this I think something wrong with the screen. So, if I show this in the side view, this is the projection P, and you have got h of the window height over a certain level, and then this is the sun's ray. So, you have got a y. It is not that it is uniform throughout, but nevertheless, because this sun's ray could be towards me, away, but in the projection looks like a line. Okay? It could be a pencil, or in other words moving like this to like this. So, consequently, how much is the lit area will depend upon the time of the day and the position of the sun. AS will be y into W if the overhang is infinite. So, it is a rectangle no matter how much more than the width of the window it is going to have, and that you can write y will be equal to the projection P upon tan theta z cos gamma s minus gamma. I shall explain, which you can easily figure out from the trigonometry P cos theta z, because this is sin theta z by cos theta z goes up. So, this is your sin theta z into cos gamma s minus gamma, where gamma s is the solar azimuthal angle. We have introduced the azimuthal angle for the surface as the angle between the north south axis and the projection of the outer normal to the surface on the horizontal plane, whatever is the angle that. So, similarly, I can take the sun's ray and its projection on the horizontal plane, and that shall be your solar azimuthal angle, which I think it can be easily shown your angle of incidence cos theta is related to sin theta z times cos gamma s minus gamma. I think the next picture should be, yeah, you have got the tilted surface with an angle beta, and the sun's ray is coming something like this. If I take the projection of the sun's ray, and if this is your south north, then this should be your gamma s. Okay, whereas we had taken the outer projection of the surface, and this we defined as gamma. So, you can the same picture is shown over here, where it looks like alpha A, but that should be gamma. Okay, it is a gamma s, RS is gamma s, that is the sun's azimuthal angle. So, my shaded area for the rectangular shape, because the overhang is infinitely long, PW simple trigonometry upon cos theta. So, my Fi is 1 minus A's upon AW equal to 1 minus P cos theta z by HW cos theta, because AW is HW into P. So, that is what you will get. AS is equal to P into whatever is y equal to 1 minus tan psi by RB, because cos theta by cos theta z is nothing but RB, and P by H W of the window is nothing but a tan psi, where that angle psi is shown. This is the sun's ray, sun, this is the projection, this is y, and this is H W, and if I draw a line like this will be psi. Okay. So, to indicate that it is for an infinitely long overhang, so we f I bar infinity equal to integral omega SR omega SS IB RB times Fi 1 minus tan psi by RB d omega upon the total radiation IB RB d omega omega SR to omega SS, which shall be omega SR omega SS IB times RB minus tan psi d omega by integral IB RB d omega in the limits omega SR to. This we have done number of times, and RB psi is fixed for a given geometry. So, consequently, it is not difficult to analytically evaluate this expression, which has been done. Only thing is, the assumption is that the overhang is infinitely long. So, you have got IB RB Fi is IB RB minus tan psi, which shall be IB times in general A plus B cos omega plus C sin omega, it need not be south facing, by cos theta z cos phi cos delta cos omega plus sin phi sin delta minus sin psi by cos psi. So, what I can do is IB times RB minus tan psi, that is what you have here, should be equal to IB by cos psi times A star plus B star. You can work out this algebra, it is not difficult. I am rewriting sin omega upon your cos phi cos delta cos omega plus sin phi sin delta. So, beta star is beta plus psi, and A star is same as your ABC, except that beta is equal to beta star. You recall the fundamental definition, sin delta times, when we expressed cos theta is A plus B cos omega plus C sin omega, that is what we have done here. Sin phi cos beta star minus cos phi sin beta star cos gamma. And here I am somewhat doing little faster than what I have done so far, because by now you should be familiar with the angles, and this is nothing but just mathematical manipulation. So, you start with the equation and put on cos theta, cos phi, cos delta, psi, etc. You will get this result, and the final answer will be so simple. You really don't have to calculate all these things. But this shows the basis. I have put it in terms of a star, b star, c star, where your slope is not beta, but beta plus psi. That is the whole idea. And you have got IB times RB minus tan psi from the previous equation, IB by cos psi. Cos psi is that angle, you remember that, cos theta star by cos theta z, which will be equal to IB by cos psi times RB star. So, this RB star is the tilt factor for the what we call the shading plane. If this is the overhang, this is the window, this will be the ASHP, the so called shading plane, right. It is nothing to, not the sun's ray casting a shadow, just draw the tip of the projection to the base of the window, you will get the shading plane. The whole idea physically is whatever is the radiation entering through this will reach the window. So, you estimate the solar radiation based upon this ASHP or the area of the shading plane, that if it is converted back into the per unit area of the window, you have your answer. So, this Fi bar infinity is 1 by cos psi integral IB RB star d omega by integral IB RB d omega, and where your cos psi is nothing but the height of the window by the diagonal p squared plus hw squared, which is nothing but the area of the window by area of the shading plane. Okay, ASHP right. So, that is what I have shown in this picture. The sun's rays will hit the window at some y distance away. Total height of the window is W, HW, and the angle subtended between the projected projection and the base of the window is the shading plane, or the area is ASHP, which can be given in terms of the geometry P and HW. So, this you can write it as A shading plane by AW RB bar star upon RB bar. So, in other words, the concept of the shading plane or the shaded area has been brought into the average daily or monthly average daily shading factor Fi bar infinity, which should be the ratio of the shading plane to the window area, which is purely geometric, and RB bar star will represent the how long the projection is and what is the height of the this thing, it will window, and RB bar is for the simple window. So, with this you can calculate your Fi bar infinity, and if you want to calculate Fi bar, I have already mentioned the problem of integrating between omega SR, omega 1, omega 2, we do not know how many, up to omega S piecewise, and then the corresponding A lit or A SHP. Okay. It will depend upon the shape of the shadow on the window. So, this is a little tricky business. So, what people have done, particularly the work at IIT Kharagpur, calculate numerically this Fi bar versus Fi bar infinity, some curve will be there. I do not know whether it is increasing or decreasing, but we know that Fi bar should be less than Fi bar infinity. When the projection is infinitely long, it is a complete rectangle, or the height or rather the line so it may be rectangular or it may not be rectangular as shown over here. Okay. So, but nevertheless, this area A lit and A lit 1 and 2. So, this I will say infinity, infinity, and this is finite. So, A lit 2 is always greater than A lit 1. So, in one sense my shading factor here will be underestimated or rather than overestimated. It assumes that more area is covered rather than the less area. Okay. So, that is about it. So, in a nutshell, when we are talking about the passive systems, most of them operate on greenhouse principle. You let in the solar radiation, but let the not emitted radiation at a wavelength longer, it will not escape, right. It could be a solar still or a solar cooker or the traditional greenhouse itself. Of course, the solar pond comes under a different category, it is not the greenhouse principle. So, this is basically keeps warm, lighter water by increasing the density by salt dissolution. Then you have got something like a trombe wall, which is basically a hollow wall where the return air from the room will be circulated and heated by the exposed sun's rays, and then your greenhouse can be adjacent to the building, which supplements rather space heating. So, you may have a small thing outlet over here. Here, in addition to the plants or whatever, drums of water, which will gain heat during the day, will release during the night, keeping the room or the house, attached house, warmer. So, this is a standard practice, or you can have a little garden in the winter months, it does not die out, and you will also have some space heating by this mechanism. Then we considered the importance of overhangs. In a nutshell, you can calculate the radiation received by a window of height h w and width w through a overhang of projection P by calculating radiation entering through the shading plane, defined as the plane between the tip of the projection to the base of the window. Okay. This can be a solid line. So, this is what it is, and sun is somewhere here. So, your RB concept and RB bar concept can be extended. Of course, generally this is beta is equal to 90 degrees and this is your psi, the additional angle. So, essentially it is a surface tilted with 90 plus psi or beta plus psi in general, and you calculate whatever is the radiation falling through this, it will reach the window. We did not do much about the wing walls, that is what I was, but you can expect, and it has been established, if this is the wing wall, you make the shading plane from here to the other side of the window. Okay? In other words, you have a I do not know whether the sketch is giving the impression, it should be the other way around perhaps. Let me try. Yes. So, from here you join. So, this will form the shading plane in the case of a wing wall. So, you can say the same thing, in other words, you change gamma for the wing wall. essentially you can summarize overhang changes beta and the wing wall changes gamma equal to whatever it is to some gamma dashed, which you can easily calculate because you know the projection of the wing wall and the width of the window. So, this is what we have achieved in terms of the what shall we say, the passive systems. So, what we shall do in the next lecture is I will try to summarize all our equations and the devices and the methods we have studied, and one thing you should remember is this could be the topic wise the last lecture, the next one will be the summary only. There could be some mistakes either in writing or original typing. So, what I would suggest is in case you find a mistake, contact me immediately at your earliest at my email address vvs.murthy@iitkgp.ernet.in. I shall rewrite it in bigger letters. Okay. So, you can send an email to this address with your specific query, and in case there is you find that some formula or some sign is wrong or something like that. This is not a coaching attempt. In other words, I will not solve your problems for you. I may indicate how you can solve a problem if you write to me with the correct data, etc., and having done your homework, but nevertheless I have to take the responsibility if there are some mistakes either in quickly writing on the paper or in my original cut and paste from my class notes. Okay. So, for that I am answerable and I shall answer you maybe if not 24 hours within 48 hours. Okay. So, please make use of this, and that is the best way I think we can improve the material and make the corrections wherever they are there. And of course, one of my professors used to say that he will give $1 for every mistake, but I do not make any such promise because I am likely to go bankrupt if all of you claim $1 each for each mistake. Okay. So, feel free to write to me, and that is one way I can help you and you help me in correcting if these are any mistakes, or also try to present in an alternate manner in case you have got a confusion. That will help in the long run for teaching of this course to the future students. Thank you very much, and next we shall go to the summary of all what we have done. Thank you.